back. So let's welcome Professor Ong to give his second lecture on topological insulators and quantum anomalous Hall effect.
So in the second talk, I'm going back to the time reversal invariant Z2 topological materials because I want to build up to the quantum anomalous Hall effect. Is the mic on? Can you hear me? Okay. It's all on.
This, yeah.
It's on.
Oh yeah, sure.
How's that?
No.
It's not on.
Over now?
Test. It's on?
You gotta make it loud, you have to turn up the volume.
Yeah, I think the volume got turned down. How's that? Okay. So I'm going to start with the, well, this hardly needs an intro. I call it an odyssey for reasons that will become apparent. And I really want to celebrate the achievements of the solid-state chemists in this area. Then I'll turn to how we know it's a Dirac fermion on the surface, and so I'll discuss the quantum oscillations. Well, of course, from the RPS experiments, there's hardly any doubt that these are dispersive, massless Dirac particles. But when you do transport, you tend to pick up everything, right? You tend to see the bulk currents. And so part of the odyssey was actually working with the chemists to separate out the surface conductance. Then I'll rapidly move on to the second half of the talk to breaking of time reversal symmetry. And I will then touch base with what Charlie Kane and Ed Whitman talked about, how the edge state quantum Hall effect arises when you break time reversal, and then show some new data on tunneling between Chern states. And so this was a bit of a surprise. I'll show you the data and get your opinion. All right, so all of us have heard about the time reversal protected surface states of these crystals. So the theory tells us that the crystal, if you have properly prepared it, should be insulating in the bulk, but it will have these very highly conducting surface states, and they are immune to backscattering. So roughly speaking, the electric field and the magnetic field form a triad with a K vector. The magnetic field is the effective magnetic field that arises, well, depends on the Hamiltonian used, but in the Rashba Hamiltonian, that magnetic field locks the spin, so you have this helicity, right, of the spin on each surface, and they rotate in opposite directions. So this is a sneaky way that nature overcomes the fermion doubling problem. It basically splits the spin degeneracy by locking one spin to the momentum, like so, and then the other degeneracy is on the opposite surface. And because of this spin locking to the momentum, backscattering, which is the main process that relaxes a current, is forbidden, 2kF, although it can still scatter over a large angle. So all this, I guess, is now familiar from all the review talks. Now, so we've heard about mercury cadmium telluride from Armin's excellent talk. That is a quantum spin Hall effect, right? So that has helical edge modes. Spin up goes right, spin left, spin down goes left. Now we're talking about a surface, and we still have helical modes, but this time the states are spread around the circle on the surface, family circle. And the system that actually was discovered very early in the game and continues to dominate this class of topological materials, all based on bismuth chalcogenites. So bismuth selenite, tellurite, and so on, and even a little bit of sulfur, which is actually very unfortunate because bismuth is probably the least understood of the elements, and it's very fickle and finicky, and it's been in Odyssey trying to control it, to wrestle it to the ground, so to speak. Now let's see why bismuth is such a favorite. It's because the P wave, the P states of bismuth and the P states of selenium, for example, if you turn up the spin orbit coupling, they invert. And band inversion, as we've learned, is one of the key ingredients in this area. So this is a calculation by the Stanford group showing the bending and the inversion that happens as you crank up the spin orbit interaction lambda. So, both Stanford and Princeton groups did ARPAS and confirmed that these are indeed excellent topological insulators. The only problem for experiment then is how to clean up the bulk, because these early crystals were very conducting in the bulk, and so even if you brought the crystal width down to a micron, it would still be 1,000,000 times more conducting than the surface states. So this has become a long track, and I just want to summarize and celebrate the contributions of Bob Carver. So that's Bob Carver and his team of postdocs and students, that's Vincent Hoare, now in Missouri, and Satya Kushwaha. Okay, so in the very early days, we worked with bismuth tellurite. This happens to be the first material, one of the first, where you could tease out this very tiny quantum oscillation signal. And that took a lot of hard work. But anyway, you could see it. But look at the bulk resistivity at the lowest temperature. So as you treat the sample correctly by thermal annealing, a class of them will show this upturn, right, indicating that the bulk electrons are freezing out as you cool down. But nonetheless, there's still a sufficient number around that they pin the resistivity to about 10 milliohms centimeter. Now that's high for a quote metal in the bulk, but still it precludes any serious investigation of the surface states. Then Bob had the great idea of doping with calcium. So calcium goes in there and sucks up the remaining carriers in the bulk, and you can see the bulk resistivity now increasing by a factor of 8. And then we were sure that we are now seeing the surface conductance, but the act of doping with calcium introduced so much disorder because it goes in as a charge of purity that it basically killed all the quantum oscillations on the surface. So we can gate it and move the thing around, but we couldn't see any surface quantum oscillations. Then Bob went back to the books and he came up with this new compound. Now it's 3 elements, right? Basically, I forgot to look at the. So all these families are based on quintuplet layers. The red balls are the bismuth, and they are always sandwiched between 3 planes of the chalcogenite, tellurium, or selenium. So in this new family called BTS, so here's the problem that Bob's trying to solve. That tellurium often gets exchanged with bismuth. That's one type of defect. And the other defect is that it's easy to create vacancies. So the idea that Bob had was that what if you replace the middle layer of green atoms with selenium, but retain the tellurium at the outer layers? And this worked for some chemical reason. And you now have a bulk resistivity that is 500 times higher than the starting materials. And so this immediately allowed us to see beautiful quantum oscillations that we could identify with just the surface. Right? So this is now about, maybe 50 times larger in amplitude than the initial heroic experiments. Next, again, Bob thought of this beautiful idea of introducing tin. Tin is very strange in the chalcogenide. No one really understands it. It creates a resonant impurity state close to the Fermi level, and that tends to soak up the remaining carriers. Well, there are chemical reasons, but I don't find them that convincing. But the proof is here. The proof is in the pudding. It works. Furthermore, Bob's team has introduced antimony, and that's because the Dirac node, we can see in RPES, is actually buried at the top of the valence band. So we need to lift this Dirac node out of the valence band, and antimony does the trick, so that it counts for antimony. Tin is to soak up the remaining carriers. And now you see 10,000 times higher resistivity than the starting material. This is going to be the workhorse, and experiments are still ongoing, so I won't show you any results.
Is this sulfur instead of selenium? Is that right?
Sulfur, yeah, that's right. Yeah, that was the other trick, using sulfur. It's not quite Moore's law, but it's not too shabby, right? 10,000 in 3 years, and if you extrapolate even conservatively, you might reach even higher factors. Anyway, so that's that's what solid-state chemistry brings to the table. Sometimes the physics is not so well understood, but it seems to be very effective. So here's the BTS material, without antimony, and I went through this already. Yoichi Ando had the same idea, roughly at the same time. And as I said, you can see these beautiful quantum oscillations. So there are tricks you can do to tease up the surface current, and you can, from the damping essentially of the quantum oscillations, you can extract a fairly high mobility, several thousands, and you can also infer the bulk mobility. So there's this factor of 100 or so between surface and bulk, and this is true of all the new generation of crystals. That, I think, is a clear indication that this 2kF suppression, the backscattering suppression, is really at work here. And note how low the carrier density is. Now it's down to 10 to the 15, 10 to the 14. All right, so I want to talk about quantum oscillations, because that has been a very powerful tool to convince us that we are seeing surface electrons. So this is just to remind you of a few well-known facts, right? So Dirac density of states is, actually this should be quadratic. In 3D, it's linear, but in 2D, did I say that wrong? In 2D, it's linear, sorry. And in 3D, it's quadratic. But you apply a field, and the Landau levels are not evenly spaced, they vary square root. Anyway, so at moderate fields, your chemical potential is here. And as you increase the field, the degeneracy increases, and therefore, with the same number of electrons, you would drop the chemical potential, right? So every time the field increases and you empty out a Landau level, the resistivity goes through an oscillation. So this is how you count, except you don't know what the number is, and that's the difficulty. You just know that it changes by an integer every time you see a peak. Here's an easy way to understand this Berry phase shift that distinguishes between Schrodinger electrons and Dirac electrons. I can couch this in Berry phase and so on, but here's an easy way that you can basically show to your grandmother, and I'm sure she'll understand it. So you recall the quantum Hall effect. You have, let's say, Landau levels like this, and when you approach the edge, you approach the edge, the Landau levels bend up, and if you put your chemical potential here, where it intersects the edge modes, those are the conducting channels. So in this case, you have 3 Landau levels below that are filled, and that gives rise to 3 edge modes. So you measure 3 quantum units of Hall conductance. So if you then look at the quantum Hall steps and count, right? So every time you fill 3 levels, you have let's say a maximum in resistivity. Then as you count down, your curve, your experimental curve plotted against the integers would then go to 0 exactly when 1 over b reaches the limiting point. Right? So experimentally, right, the thing that distinguishes between the two is that in infinite field, when 1 over b goes to 0, in the Schrodinger case, you have to be stuck in the lowest Landau level. There's nowhere else to go, right? Whereas in the Dirac case, you are actually stuck in the middle of at the node, right, which is between 2 steps. So it could be here or it could be here. So this line, which plots 1 over bn versus the integer, has a negative intercept. So I think this is the easiest way to understand how this arises, be it graphene or these Ti materials. So in one case, 1 over bn is proportional to n, but in the second case, it's proportional to n plus a half. So to repeat the point, so you would go in there and plot the 1 over bn. I've tilted the axis, and if you plot them against the integers, you should see it terminate at 0 if it were Schrodinger gallium arsenide, or it should have a minus a half if it were Dirac. And this corresponds to the Berry pi phase shift. Now, in these new materials, that's when we start to see the quantum oscillations really clearly. Here, we've gone to very high fields, 45 Tesla. Show somewhere here. Anyway, if you invert this number, that corresponds to 45 Tesla. And now it's ringing like a bell. I mean, there's so many oscillations and you have no problems making the index plot. And from that, you can pull up the integers, right? So the 1, 2, 3 indicates the Landau level that you've just emptied at that field. The mobility, which is extracted from the ring down of the amplitude, is about 3,000. So the index plot, as mentioned, you can track it now with all these curves, all these oscillations, and you see that the extrapolation does give you minus a half. So this is the first time that we convinced ourselves that we were actually seeing surface electrons. Now, another way to do this is to gate it. But, gating is really only efficient when you have a very thin film, as we'll see in the second half of the talk, or you have almost semiconducting electron gas. With these samples, you cannot use dry gating, electrostatic gating. The gating basically terminates in the Thomas Fermi screening length, which is only a few angstroms. Right? But chemists have developed this method called ionic liquid gating, and what you do basically is you immerse the sample in this organic liquid, and you apply a gate voltage on a gold electrode, and the ions separate, and they essentially coat the electrodes with a layer of charge. And this it applies a very intense electric field on the sample. And this works. The only problem is that you can only do it a few times because the stress, as you cool down, right, the liquid around it freezes, and actually it starts to pull the crystal apart. So you can do it maybe 5 times, and you have to set the voltage every time. So this is a painful, non-reversible kind of experiment. But nonetheless, it worked. And using this, my student, Jun Xiong, could actually tune the surface oscillations in a bulk crystal. So you can sort of see that the rapid oscillations now basically spread apart, right, as you pull the chemical potential down towards the node of the surface Dirac states. The longer the period means that you have a smaller Fermi surface caliber. So you can see that the amplitude increases, and at the same time the period increases. Here's a better example where he's also Jun has taken it to very high fields, 35 Tesla, and you can see again the oscillations spread out in field as you decrease the surface caliper, Fermi surface caliper. So you can do the same Landau index plot, and again, now this time it goes nearly all the way to, I think, n equals a half. And it still terminates at the minus a half, right? So again, this confirms that you do approach the Fermi, the Berry phase shifts expected from massless Dirac electrons. Unfortunately, because the Dirac node is buried in the valence band, we could never get it, we could never cross the node. And it took us a long time to realize that what happens is that if you keep increasing the gate voltage, it just saturates. You can never pull it to this point. So that's what led to this new program of introducing antimony to lift the Dirac node above the valence band. And unfortunately, those experiments are still ongoing, and so I don't have anything to show. All right, so that's all right. So that is when time reversal is preserved and the Dirac node is protected, right? So now I want to change gears and talk about breaking of time reversal and basically exploring the quantum anomalous Hall effect.
Can I ask a question?
Yeah.
What's the mean path for the
Okay, can you speak up? I didn't hear.
the mean free path, roughly the best mean free paths that you get for
The mean free path, I think at the numbers, I think they're around 1,000 angstroms, maybe 5,000 angstroms for these new generation of crystals. Okay, so let me repeat the discussion of Cramer's theorem. Like Charlie, I find this fascinating. It's like a haiku, because the Cramer's theorem can be stated in 2 lines, and but it's no longer in the textbooks. Cramer's theorem was very big in the era of atomic physics, when people were first exploring spectra, and also in the transition metal oxides. When I was a graduate student, that era ended, right? When every physicist was doing electron spin resonance, paramagnetic resonance, and this is big. But now it's come back. It's come back because of the protection mechanism. So let me just repeat what Charlie said, right? So suppose you had 2 partners of time reversal. Theta is the time reversal operator. Then they must have this relationship because theta squared is -1. So these are all 2 spinors. So spin is in there, right? And you then perform the time reversal symmetry on your crystal and you compute the matrix element. Then since it's anti-unitary, you get that you simply get back the same matrix element but with the partners reversed. But then if you incorporate this into the left-hand side, you get minus psi and phi, right? So that proves that these 2 spinors are orthogonal to each other, and therefore they're distinct. So if you start off with time reverse partners, they must be orthogonal, and that is Cramer's theorem, right? So therefore they are 2-fold degenerate. But now, in the context of topological insulators, let's look at these 2 Dirac bands that RPES shows. Having these 2 being present, we need to convince ourselves that they are protected, right? So any matrix element that is time reversal symmetric, you can repeat the same argument and show that these matrix elements must rigorously vanish for the same reason. Right, basically because we can now treat V times psi as yet another time reversal invariant wave function. So this protects the node of the TIs and all these beautiful physics that we've heard about. But now the flip side is that now if we introduce a magnetic impurity, magnetic dopants, or a ferromagnetic state, then the gap will open, right? And therefore, we will have opened the gap on the surface of massless Dirac states, converting them to masses. And then just to repeat, perhaps in a slightly different way, the discussion by Charlie Kim and a little bit by Ed as well about the Hall conductivity. So I want to show that the Hall conductivity is an edge mode that is half a quantum of the Phuan unit. So we start with the TKNN expression. The Hall conductivity is basically the Berry curvature, the flux of the Berry curvature in the Brillouin zone. And now if we take a massive Dirac state, that's the one that we want to create, right? We're opening a gap here. Then you can write it in this form, in the pseudo-magnetic field D. And you see that for this node centered at the gamma point, D will be a Maron-like distribution. Well, you have to regularize it so that it falls off to 0 and far away. And now you do this famous mapping to the unit D sphere. It only covers half the sphere. And therefore, the Chern number is a half, and that immediately tells you that the Hall conductivity is 1/2. So when you open a gap, you should see half a Hall quantum flowing at the edge. And moreover, now you've broken time reversal symmetry. This is purely chiral, right? So it flows only in one direction. All right, but it's very hard to see that because of this doubling problem, and this is one area that experimentalists are still chasing after. Nature seems to hide this 1/2 very well. So one way that you can see that is that now you take a crystal, could be a thin film, and you imagine you can open up the two surfaces like a book, right? And initially they were both up in magnetization. And now you see that this one is down. And therefore the two circulations are opposite to each other. So at the domain wall, which are the sides of the crystal, both of them are parallel, right? So you see that 1/2 plus 1/2 is 1. So you always see 1, basically. And if the crystal is very thick to begin with, you would have a lot of helical edge modes. And these modes are not protected. They can backscatter against each other. But if you make the crystal very, very thin, the helical state should disappear, and all you should see is the one quantum of Hall conductance. So this was proposed a long time ago by the Stanford group and also by Kane and Fu. And so the race was on, right, to find this effect. And the group that finally found it was led by Chigun Shui and my former student Yayu Wang, with help from Lilu and IOP. So what it involved was basically what I mentioned, that the program that Kava was engaged in. It's a combination of bismuth and antimony, right, to lift the node out of the valence band, and then tuning the compositions of all 4 elements, tellurium, selenium, bismuth, and antimony. And they must have marched through 200 samples. Eventually, they found the exact composition that works. So there are 5 elements, actually, because you need to introduce manganese or chromium. Eventually, they use chromium to make it go ferromagnetic, and that opens a gap and leaves behind, so as shown here, leaving behind this chiral state on both the upper and lower surfaces. Now, you cannot use standard wet lithography to etch the sample, so they introduced this, what now people call cutting-edge technology, which means using a needle under computer control to scratch out the part of the sample you don't want. But this worked beautifully, and you can sort of see that the early results show that as you, I think this is temperature, yeah, as you cool down from 80 Kelvin to 1.5 Kelvin, you're starting to see the Hall effect take on this characteristic anomalous Hall effect profile. We're not quite there yet because the temperature is way too high. But eventually, you see this, this profile. And it's beautifully quantized. So let me just walk you through it. So the temperature is very low, 30 millikelvin, and you have tuned by gating, you have tuned to, to drop your chemical potential into this mini gap that you have introduced. And the Hall effect is, practically unresolved from -1, jumps, and then goes to +1, right? So those of you with good eyes will notice that there are two lines here, and it's because there's this coercive field, which will become more apparent in the next slide. At the same time, the rho x-axis is close to 0, so it's dissipationless, but it starts to dissipate when the jump happens. Okay, maybe I should show the expansion effect. So, right, so here they are varying the gate voltage to move the chemical potential into this mini gap, and when you hit the gap, it shows this fully quantized Hall effect, and at the same time the resistivity becomes dissipated when it's transitioning between the two churn states. Okay, so when we saw that, we realized we've been focusing on crystals and not enough on thin films, because that's where some of these beautiful physics can be really explored much more effectively. Now I'll show you some new results where we team up with a group in Penn State led by Nitin Samar, using samples grown by NDE by Tony Ricciardello, former student of the study. And I'm going to show you some of these new results. So there are currently about 5 groups worldwide that have managed to duplicate this experiment. And okay, so here are the results. So the trick was the following, which we should have realized from the start. That when you grow these samples in MBE, when you bring them out of the vacuum, the surface starts degrading. It exponentially degrades once you remove it from vacuum. The trick is actually coated in situ with 2 monolayers of aluminum. Right, so aluminum will cap the layers, and the moment you expose it to air, it turns to aluminum oxide, which is the best insulating material in the world, right? So aluminum oxide then acts as the cap, and once we realized that Tony could grow beautiful films, and these are now quantized to a degree much better than the Chinese scientists. So I just want to show you some benchmarks. The films now are 10 quintuplet layers thick, that means 10 unit cells of this bismuth tellurium layers, as opposed to 5 in the Chinese samples. All right, so when you run the field through, the Hall resistivity jumps, right, from -1 to +1, and the dissipation channel, the RXX, shows 2 very sharp peaks. Now, to show you the benchmarks, I'm going to amplify the plateau, which is shown here, right here. And you can see that the resistivity really clings to the von Klitzing value to a few parts in 10,000. So in fact, the error is mostly from our voltmeters. We don't have these $1 million calibrated voltmeters. They are usually good to 1 part in 10 to the 4, and that's the residual error. So it really clings to this quantum beautifully. It really makes you believe in quantum mechanics, because this is a sample that is a millimeter in size, and you can really see the quantum. At the same time, the dissipation drops, right? So this looks like it's 0, right? Here's 0. But it's actually very, very close. Between, it comes to within 3 parts, again, 3 parts of 10,000 of 0. So it's almost dissipation. This tiny peak here is a bit mysterious. We think it's from the quenching of superconductivity in the indium context, but it needs some rethinking. We hope it's intrinsic. If it were intrinsic, then you would have seen superconductivity in these topological insulators. But it's unlikely because it's in a ferromagnet. Anyway, this is a topic of further research. Now on the left here, I'm going to show the theme of the rest of the talk, where we think, the corresponding inflation that comes from tunneling, right? So what's happening here as you reduce the field, once it goes to zero, then the system is unstable. The magnetization is pointing the wrong way with respect to the applied field. So it knows it has to cross. And whether it does it by diffusion of a domain wall, as is common in ordinary ferromagnets, or by tunneling, that's the interesting question. Okay, before we get to that, so some ways to characterize these new samples. The Hall effect, as we get away from optimum, starts to deviate from the quantum, and it's shown here. What's more interesting is that the dissipation grows exponentially as you lift the chemical potential out of a mini gap. This is on log scale, so you can see that it grows exponentially. And this is a bit of a surprise, actually. It shows that this quantum anomalous Hall effect state is protected by a gap, but the gap is very tiny. All right, so here's the evidence. I think this is there. Let me just point here. So as you change the temperature while sitting at the optimum gate value, you see that the conductivity, or I've just inverted the resistivity tensor, is activated, thermally activated. But the slope is very small. It's only 200 millikelvin. 200 millikelvin corresponds to 20 microvolts or so, right? So this is very odd. But remember, we're talking about a two-dimensional ferromagnet that shouldn't actually have a long-range order, right? But nonetheless, it is breaking time reversal symmetry and opening the gap at the Dirac point. So this is versus temperature. If you now fix the temperature at 10 millikelvin and change the gate, so you're moving the chemical potential, again, you see this logarithmic, this exponential increase in dissipation. So again, the same gap, right? So there is a possibly many-body gap protecting the quantum anomalous Hall effect. It is very tiny and it is very mysterious. So this, hopefully, theorists will find interesting. All the groups should see that. I've checked with Yayu and Tsinghua, as well as the Stanford group. They see this gap of the same size. But that's not what we're interested in. What we're interested in is this new phenomenon, right? So what we're doing now is to explore how does the system change from magnetization down, which is unstable, to up, which is the stable state. And thanks to the experimental skills of Minhao and Woody, this experiment, it burned tons and tons of liquid helium, but it's well worth it for reasons that I hope will become apparent. So they noticed that whenever they go through this transition, it jumps. And initially we thought it was just stochastic noise, but the pattern is as follows, right? So each of these curves is taken when you prepare the sample here, and then change temperature, fix temperature, and then gradually sweep through zero, and then you keep going. This is a painfully slow sweep, and then the system will jump at one particular field value, and that jump field is very dependent on temperature. So when it's 70 millikelvin, it jumps here, then at 100 millikelvin, it jumps here, 125, it jumps here, and then it keeps going up. But you notice that the amplitude of the jump diminishes. So that, at 150 millikelvin, it's still jumping, but the amplitude becomes so small, we can't resolve it. So these are very puzzling features, and we spent close to 6 months exploring this. And that's what I want to show you. The jumps happen on a very fast time scale. So Minhao removed all the filters in this dilution fridge, leaving only the low temperature filters, which have a time constant of 1 millisecond, and the jump is probably faster than that. We just cannot see it. It's too fast. So something's happening at a very, very short time interval. See, it's much more noisy here in the trace because all the filters have been removed. So here's a broader scan of the jump phenomenon. If you are very cold at 10 millikelvin, you don't see these jumps. You start to see maybe the precursors, some wobbling here, but pretty soon it's a smooth transition, right? So this is the transition from -1 churn state to +1. But then as you warm up towards 70 millikelvin, you start to see the jumps appearing, and this is the panel I showed you before, right? And I emphasize that as you raise the temperature further, the jump amplitude diminishes, so that while it may still be occurring, but we just cannot see it. And this remark will become important later. If you go now to even higher temperatures above 150, then everything is smooth again. So this behavior is pretty much like what you would see in the standard integer quantum Hall effect in gallium arsenide. So it's smooth, and this is probably interpreted correctly by this the domain formation of the quantum Hall states. Let me ignore this panel for brevity. Of course, since the two channels, dissipation and Hall, are interconnected, intimately connected, you see the jumps as well in RXX. This was the delta function of dissipation at the transition, but now I've amplified the horizontal scale. At 10 millikelvin, it's pretty smooth. A few little wiggles here, but it's pretty smooth. But then at 70 millikelvin, you start to see the jumps at the leading edge. And when you're really into the temperature regime where the jumps are very big, you see that it stacks up and it stacks down. So it's kind of a curious pattern. All right, so the first clue about what's happening derives from plotting the jump field, right? So this is the field at which it first jumps when you slowly go into this field reversal regime. That's a function of temperature, and you can see that it increases with temperature. So that suggests to us it's a tunneling phenomenon, right? So if you trap the standard way of understanding metastability is to have the system, the red particle, trapped in a metastable well, so it wants to get to this other well. And if it's thermally assisted thermally assisted hopping, the higher the temperature, the easier it is to get over the barrier. So it should happen at lower fields rather than higher fields. Remember, as you increase the field, you are lowering the barrier that's trapping the particle, right? So this is opposite to that, and very strong evidence for quantum tunneling. What's less obvious is the jump amplitude. It's confined to this window of temperature between 50 millikelvin and 150. We don't really have an explanation for that at the moment, but I can share some guesses with you in a second. But notice that the jump amplitude, when it really gets going, is close to 1. It should have been 2, right? Because if the system were tunneling, nothing should stop it from going all the way from -1 to +1. But it stops at 0. And that, I think, is kind of interesting. Okay, so that's those are the points. Now, you can also look at the spatial pattern, right? Because there are many contacts on the sample. So you can look at when the jump first occurs in one pair of Hall contacts, does the other pair respond, right? So Min Hao and Woody have done many such measurements. I'm just pulling out 4 examples here. So these are, we're always passing current between 1 and 4, and we are monitoring, any pairwise combinations of the voltage contacts. So if you look at the Hall channels first, when 5-3 jumps, 5-3 means this pair, so that I call the downstream pair. 6-2, the other pair barely notices, that's a little bit of a glitch. But then it waits until the field is more favorable, then it jumps, and in the meantime, 5-3's jump is not as dramatic. And so you can see all these correlations between the initial jump and the second jump, as well as in the resistance channel. It jumps up, then it jumps down, right? So this suggests the following, at least this is a zero-order attempt to understand it. We've used the Landauer-Buttiger formalism to calculate the resistivities and the current. This is led by Jian Li, who's in the audience. Along the lines that Amir discussed, and this is sort of the standard way to understand edge conductance in quantum Hall effect. And you can pretty much duplicate the pattern that we see, except for one drawback, which I'll point to. You see that the downstream Hall pair jumps first, and then it's done, right? And the second Hall pair jumps later, and the second jump. Meanwhile, the dissipation goes up and comes down, and the opposite happens to the other pair, right? So without going into the details, this is a well-known Buttiger formalism. If we set all the transition matrices to 1, and then allow scattering between the channels. Remember I mentioned that at the domain wall, and these are domain walls, the 2 currents are parallel, so they can scatter between each other. That's always the case that leads to the dissipation. At least that's how we understand from the quantum Hall effect. So this pattern, the jump happens here because the domain wall, let's say it nucleates at one edge, it jumps to here, right? And then at the second jump, it goes even higher. So these very large jumps are consistent with macroscopic displacement of the domain wall. And as I mentioned, it happens on a very fast time scale. So all these patterns seem to be evidence, and I know this is speculation, but it seems to fit all the experimental facts, of tunneling with tunneling-induced expansion of the true vacuum. So many of you are doubtlessly aware of this classic paper by Coleman and then Calvin and Coleman, taken up by Leggett and Caldera. Now we're not talking about quantum tunneling of a single degree of freedom, right? That would be quantum mechanics. We're talking about field tunneling or field configurations. So you need to bring all the quantum field theory apparatus to bear to summarize the result. The action is it's the usual standard action for magnetization. So phi represents the magnetization. Now you introduce a potential that depends on the configuration on phi, and you design it so that it imitates a metastable state. And so the Feynman paths will have to go all over the place, but it's clear that it doesn't change this picture very much. But then there will be Feynman paths that go into imaginary time, right? And that involves this Wick rotation, imaginary time, as well as a inversion of the potential. Then suddenly the system finds that this path is also allowed. And this Coleman calls the bounce. And today we call it instanton. And so it spent a lot of time sitting here, and then every so often it would rapidly go through this bounce and end up in a metastable state. And I think this is what's happening. If you go into the Wick rotation, Euclidean space, it's easy to see that you would get a hyperbolic tangent, right? So between the true ground state and the false vacuum. Now if you convert the solution back into real space, that predicts a hyperbolic expansion. Okay, and that's the prediction of Coleman that if our universe had been trapped in a false vacuum after the Big Bang, we should see an expansion of this bubble at the speed of light. And they said that, well, this would be occasion for anxiety. But luckily, this doesn't happen. But then this whole thing became fashionable in the era when the LHC was being turned on, right? Remember that? So this became, again, a flurry of interest. But I think most of these apparatus is now useful for condensed matter. So, okay, before I say that. So here's the scenario, right? So the system is trapped in a false vacuum everywhere. And then there's a bubble where it initiates. And once it gets out after the instanton, it should expand and cover the whole sample. But it doesn't do that. That's because what's missing is dissipation, right? So Caldera and Leggett imposed dissipation, but they only treated the single particle tunneling. I'll review the literature in a second. So it doesn't go, and so this raises the question, if you have dissipation by raising the temperature, does it halt the expansion of the bubble? And we would like to think that the reason why the amplitude of the jump diminishes at high temperatures is because it escapes, but then the expansion is halted before we can see it experimentally. Right? So it's too small a bubble to see experimentally. And this would be, I'll comment on this. Oh, here it is. So at the same time as our experiment, Nitin Samart provided samples to Elie Zeldorf at Weizmann. And Zeldorf had built this squid, which is very tiny. It's a beautiful experiment, actually. You have this tiny pipette that you can draw down to 200 nanometers, and you cannot see it, but these are two niobium or aluminum films with a break in between, and that's your squid. So the squid is the very tip of this pipette. And he can actually pick up magnetic flux through that, and he can do the scanning. Unfortunately, he can only go down to 250 millikelvin, which is where we don't see any more jumps in our resistance. But okay, the main finding here, which relates to our experiment, is that there's no evidence for domain wall. Nothing diffuses if you watch it at several fields. It's always the same bubble, and the bubbles flip individually. And we would like to relate this to, these bubbles are the expansion after the instanton expansion. Then it's frozen because the temperature is too high. And we would like to say that if Zeldorf can cool it below 150 millikelvin, he should see these bubbles become extremely large in the sense that in the way we see it. Okay, so to close up, let me just go through the tunneling literature, right? So in condensed matter, this of course has been explored by many groups. As I mentioned, Caldera and Leggett introduced dissipation, but only focus on single particle tunneling. Dissipation in tunneling of fields was first introduced by Philip Stam and also by Chernovsky, but they apparently haven't done anything recently. So it's not quite enough to compare with our experiment. The experiments are mostly on Josephson junctions, led by Martinez, Devoret, and Clark. Quantum molecular magnets, Barbara and Miriam Sarachik. Domain walls and transverse Ising systems, Tom Rosenbaum and Gabe Apley. And even in biological materials, although this is somewhat controversial, Oshalom claims to see quantum tunneling. But all these experiments have to do with a single entity and one degree of freedom. So there's no information on inflation or expansion. So we would like to think that this is possibly the first experiment that couples into this phenomenon of the effects that you see spreading out that you can actually study in the lab. All right, so let me end here and thank my co-workers for both talks. Thank you.
Maybe I missed it. So the amplitude of the jump, is it an actual function of the temperature or stochastic?
Okay, so there's some slight stochasticity, and if you I should have brought slides. If you run the experiment 5 times, the jumps will always happen in the same field, except for a 5% jump.
Or the height?
The height is the same too, yeah. So the curve
is it rational?
Is it?
Is it rational? Is it rational small p and q?
Rational. I thought you meant is nature rational. Is it a rational number?
Yeah, it's a fraction of -1 to 1.
Oh, that's an interesting suggestion. We have to check that. We'll let you know. I don't think it is, because we have the histogram here. Yeah. So this is basically the histogram versus temperature, and there's a little bit of a glitch here, but there's no subplateaus.
What is the source of the dissipation? Do you know what is the source of the dissipation?
We don't know. We think it's the bulk electrons that get thermally excited. So that's experimental, right? So let me just show you the experimental evidence for that. So as you increase the gain, you see that the dissipation rises very strongly. So it indicates that but this is gaining. So if you gain away from the optimum part, you see a lot of electrons being thermally excited. So that's the main source of dissipation. But it could be also the spin waves in this. Because remember, this is happening in a cumulative ferromagnet involving each other. But it's probably the unwanted electrons that are causing the dissipation.
Okay, so gift session. So it's my pleasure to present this souvenir from the Lego movie to Professor Ong, the master builder, not of Lego, but of powerful apparatus for unveiling the beauty of physics.
Thank you.
Okay, 50 minutes there, and we'll start next lecture at 3:30.